This is the PreLab for oxidation-reduction reaction. During this experiment, you'll look at both inorganic and organic oxidation and reduction reactions. First, look at single replacement reactions. These are almost always inorganic oxidation-reduction reactions.
Single replacement reactions can take place when an element is mixed with a compound in solution. Sometimes the element will replace one part of the compound. A new free element will be released and a new compound will form. The general form for these is usually M plus ZQ, which would be aqueous, will produce MQ aqueous plus Z. This is a single replacement reaction where M has replaced Z, so MQ is the new compound and Z is the new free element. Sometimes, however, there is no reaction. The metal M remains the free metal and ZQ, the compound, remains the compound. If there is a reaction, the solid metal is becoming part of a new compound and is replacing either another metal or hydrogen. That sends that metallic element or hydrogen out of its compound. When there is a reaction, the solid metal is more active chemically than the metal or hydrogen which was originally in the compound. So prepare a rack with all the medium test tubes for all the reactions ready to go at the same general time. Label the tubes with a wax pencil. Put the specific solution into each of its tubes. Use sandpaper or a wire brush to clean the metal pieces first so that fresh metal is exposed. Do this even if the metal appears clean because it could have an oxide coating or an oily layer protecting it. Add a solid piece of metal to each specified solution. Is there any reaction? Look for changes in color on or near the original solid. Any new solids forming on or near the original solid. Look carefully, they may be the same color as the original solid. And look for bubbles or fizzing of gas. Gather enough clean medium test tubes for all the possible reactions. Locate the solutions needed, locate the solid metals needed. Sandpaper or a brush will be used to provide a clean, fresh metal surface. One or more of the potential reactions may need to be viewed as a previously set up demo in the lab. Check with the instructor or the assistant about this. Remember, try to do all the potential reactions at generally the same time. Put about 1 to 2 inches of each specific solution into its own medium test tube. Prepare all the tubes. Add a piece of each specific solid metal to the solutions and watch for any reactions over about 15 to 20 minutes. Longer than that is also fine. Collect all the waste in a beaker which you keep inside your mini hood. Rinse the test tube into the beaker also. At the end of the experiment, pour the waste from your collection in the large beaker into the coarse waste jug in the main hood.
Once you have the observations that allow you to state reaction or no reaction, you can begin to rank the metals by relative activity. Remember, a more active metal ends up in a compound rather than as a free element. It is more chemically active. First, look at any specific test tube result and use that data to rank the 2 metals involved. You'll do this for 5 specific tubes during the lab session so that we can check and make sure you're getting the basic idea right. Later, use all the data to continue making ranked pairs and finally to make an overall ranking of the activity of the metals in this experiment. Then, use the directed questions in the lab manual to connect these results to oxidation of one metal coupled with reduction of the other. These were inorganic, redox, or oxidation-reduction reactions. Then, look at some organic oxidation reactions. Take time to review some organic functional groups. There are several pages in the lead-in in the lab manual that show examples of some of the important functional groups you'll be working with in this experiment. Oxidation of organic compounds is very important biologically. Both sugars and fats undergo oxidation during energy-producing reactions. These biological oxidation reactions are catalyzed by enzymes. Oxidation reactions can also be carried out in test tubes using inorganic oxidizing agents. These often contain transition metals because color changes indicate changes in oxidation state, and in that manner,
an oxidation reaction can be noted by a color change. Organic oxidation focuses on the bonds between carbon and oxygen. We can write an oxidation chain, starting with the totally reduced hydrocarbons and working all the way up to a completely oxidized carbon, CO2. Structural features limit whether oxidation reactions can take place. For example, alcohols can be subclassified into primary, secondary, and tertiary alcohols based on the number of carbon groups bonded to the carbon that has the hydroxyl OH group on it. Primary alcohols have only one other carbon group attached. Secondary alcohols have two carbon groups attached, and tertiary alcohols have three carbon groups attached. These structural features tend to limit the extent or whether oxidation will take place at all. Primary alcohols will oxidize to aldehydes and then to carboxylic acids. Secondary alcohols can be oxidized to ketones, but the ketones do not oxidize further to carboxylic acids. Primary and secondary alcohols will undergo oxidation readily, but tertiary alcohols will not.
Another example of how structural features can influence properties is seen by looking at how substitution of halogens for hydrogens on a hydrocarbon changes flammability, or the ability to undergo the combustion reaction. Here are three compounds. Look at them and look at their combustion properties. Can you see what the connection is to introducing halogens into a hydrocarbon? One of the compounds shown could even be used to extinguish fires. Which one do you think that is?
The list of compounds to be tested can be found in the data tables in the lab manual. Take time to classify each of the test compounds into its organic functional group family. Structural formulas for these compounds may be found in the introduction if you need to see these. You'll investigate combustion reactions of organic compounds.
Combustion is just a form of oxidation. Ultimately, rapid oxidation is actually combustion. This poor gummy bear is undergoing oxidation rapidly enough to burn.
The procedure for combustion is the same every time. Place a watch glass, a small one is best, on a heat-resistant mat which is directly on the bench top, and this is just barely inside the hood. Use a burning splint, not a match, but a burning splint, to try to ignite the liquid. Put about 5, a maximum of 10 drops of the compound on the watch glass. Light the wooden splint and hold the burning splint in close contact with the liquid. If the liquid evaporates before ignition, add a few more drops and try again. Determine if the liquid ignites easily or with difficulty, and then examine the combustion itself. What's the color of the flame? Are there clear or sooty vapors, and is there a residue left or not? Remember, even though it won't look hot, the watch glass will be hot. If you get a very sooty result, the watch glass may be soaked in the prep room until next week. Fire is the biggest concern. You want controlled fire, but you certainly don't want additional compounds to ignite.
Then use some inorganic oxidizing agents to cause oxidation of specific functional groups. Watch for pertinent color changes that indicate that an oxidation has taken place. You'll do oxidation with sodium dichromate, oxidation with potassium permanganate, and oxidation with Benedict's reagent. Each of these is most useful for a specific type of organic compound.
Dichromate containing oxidizing agents are very useful for alcohol oxidations and aldehyde oxidations. The rate of these reactions is not a factor to observe. What's necessary is to look for the pertinent color change from the yellow-orange of the reagent to a blue-green or deep dark color for a product positive for oxidation.
The reagent is orange. Many colors may appear during the reaction. The positive reaction ends at green.
Another oxidizing agent is neutral potassium permanganate. This reagent is purple and will turn to a brownish solid. It's actually quite ugly when an oxidation reaction has taken place. Alkenes and alkynes will be oxidized by this reagent. Also, alcohols and aldehydes will react. Saturated hydrocarbons, alkanes, usually do not react with neutral KMnO4. When a saturated hydrocarbon is mixed with KMnO4, layers will form because of solubility issues, but the KMnO4 itself will generally remain its deep, dark purple. No oxidation takes place. Unsaturated carbons, alkenes and alkynes, usually do react readily with KMnO4. The purple reagent will still layer, but it will form a brown solid or a brown layer. A technique-related complication of this reaction is that even the smallest amount of contamination with a double or triple bonded compound can cause false positive oxidations. So what about when aromatic hydrocarbons are tested with an oxidizing agent like KMnO4? Do you remember aromatic hydrocarbons? An example is given here, benzene. What happens when oxidizing agents are used on them? Are they like alkanes, or are they like alkenes, or
Guess you'll have to wait and see. Then test some sugars with Benedict's reagent. Benedict's reagent is an oxidizing agent that can pick up free aldehyde groups, oxidizable aldehyde groups, within sugars. You can read more about Benedict's reagent and the structure of sugars in your lab manual. Take some time to do that so that you'll understand the results that you're seeing.
After the bench chemistry, and perhaps after the lab session, analyze your observations by responding to directed questions requesting you to look at structure and predict properties.
There is a PreLab quiz available for this PreLab presentation.